Hello guys, I welcome to all of you in this video lecture. Today we will discuss the Euler theorem for homogeneous function. So before starting Euler theorem, I just want to give you the definition of homogeneous function. So what is homogeneous function and how we can prove that a given function is homogeneous of degree n. Okay, homogeneous function. So we start for the definition of homogeneous function of two variable function. Suppose z is a function of two variable and it is called a homogeneous function of degree 2 and of degree n if we can express the given function fxy any one of the following form any one of the following form. Okay guys, so first form is if we can prove that if fxy alpha x alpha y is equal to alpha to the power n f of xy, then we call fxy is homogeneous function of degree n. Okay, if I can express fxy in this form fx comma y, and this is equal to x to the power n gy upon x, then also we call this is homogeneous function of degree n. The next form is if we can express the given function in the form of fxy is equal to y to the power n and z x upon y. So these are the three forms. If we can express any given function in any of these forms, then we call the given function is homogeneous in nature and has degree n. The power of alpha to the alpha, here power of x and here power of y. Okay, we can understand this concept with the help of some examples. For example, suppose we want to check the function f is equal to x square plus y square. Is it homogeneous or not? So first of all, we will write it as alpha x alpha y, and now we will check it will be equal to alpha square x square plus alpha square y square. Now we can take alpha square common here, x square plus y square. So now x square plus y square is again a function of fxy, so it is equal to fxy. So here we can see that f alpha x comma alpha y is equal to alpha square into fxy. So from here we implies is that alpha f is homogeneous function of degree 2 of degree 2. Similarly, we can check the function f is equal to sine inverse x upon y. Now we will put f alpha x alpha y. This will be equal to sine inverse alpha x upon alpha y. Now we can cancel out alpha by alpha. So this is again equal to sine inverse x upon y, which is our f of xy. So we can write this is alpha to the power 0 into f of xy. So here again we express the given function fxy in the first form. Okay, so from here we can observe that f is homogeneous function of degree 0. Now I will give you an example which is not homogeneous function. For example, if we take fxy is equal to sine inverse x square upon y, then we observe f alpha x f alpha y is equal to sine inverse alpha square x square upon alpha y. Okay, now we can cancel out alpha by alpha, so this gives us sine inverse alpha x square upon y, and this is not equal to f of xy, because here alpha is 1 but here alpha is not 1. You can take alpha is any constant, so we cannot rewrite this is equal to in the form of like this. So this is not homogeneous function. Here I will give some more examples, like f is equal to x square plus xy. So if we put alpha x in place of x and alpha y in place of y, you can see this is homogeneous function of degree 2. Similarly, if we take f is equal to tan inverse y upon x, this is also homogeneous function of degree 0. The next function is f is equal to 1 upon x square plus y square. Now this is again homogeneous function, but here the degree is -2, because if we put f alpha x alpha y in place of xy, so we get alpha square x square plus alpha square y square. Now taking 1 upon alpha square common from denominator, so we get x square plus y square. So this is again f of xy. We can write 1 upon alpha square is equal to alpha to the power -2 into f of xy. So this is how we can express the given function. That means the n which I discussed here, it may be a negative number. So this n may be a negative number. Okay, so from here, so we understand that what is a homogeneous function and how we can prove that the given function is homogeneous or not. Okay, similarly we can generalize this concept for n variable function. Okay guys, so we can generalize the given in definition for n variable function. So suppose fx y z be a function x1 x2 up to xn, be a function of n variables, and it is called homogeneous function of degree n, yeah, m, if we can rewrite it is in the form of f lambda 1 lambda x2 up to lambda xn, and this is equal to lambda to the power m and f of x1 x2 up to xn. So if we can rewrite a function of n variable in this form, then we call this is homogeneous function of degree m. Similarly, if we can express the function fx1 fx2 up to fxn like this, x to the power n into x to the power m into g of x1 to the power x2 upon x1 comma x3 upon x1 up to xn upon x1, then also we call this is the homogeneous function of degree m. So in the next video we will prove Euler theorem and how